We have, of course, talked about gravity quite a bit this year, but when we've been talking about gravity, it's always been near the surface of the Earth. The law of universal gravitation allows us to expand outside of that general zone and to handle situations where we're dealing with a planet or a satellite, maybe something away from the Earth completely, near a different planet, even some other solar system besides the Milky Way. So this is a very general way of describing the force due to gravity. So the law of universal gravitation is Newton's doing again. He did a lot of work at this time with how things move and why things move. And this is sort of the famous law that has to do with an apple falling off the tree, supposedly, and hitting him in the head and providing the inspiration for this sort of an idea. And the basic law says that every single piece of mass attracts every other piece of mass, and that force is mutual, it's interactive, simultaneous, equal and opposite forces, like this diagram indicates. The force depends on how large the masses themselves are, how many kilograms of mass each has, and then also the distance between them. It's an inverse square law, so the distance is in the bottom of this fraction. As r increases, the force decreases. That's the inverse part of it. And then it's a squared law because it varies based on the distance squared. In your first exposure to this force, you might have called r a distance d. As we've worked through more things involving calculus, we discovered that d is not a particularly good formula or a variable to use, and so we do switch to r. Plus, a lot of things dealing with universal gravitation have to do with circular motion, and that circular path very often has the same r value as this formula, so it makes sense to sort of connect them. When we're working with standard units, the constant that relates all of these things together is called the universal gravitational constant. It's shown here at the bottom of the screen. You might want to jot that down. 6.67 times 10 to the negative 11th. It's a very small value. The gravitational force is really negligible if you're dealing with small objects. That's why you are not attracting pieces of mass towards you like a static electricity idea or something like that. It's a very small force unless one of the masses is really big, like the mass of the Earth or the mass of the Moon. So let's take a closer look. All right, so what if we do have a very large mass like the Earth or the Moon, and maybe even looking at the attraction between them? This law officially deals just with the particles. But if your particles are more than particles, okay, if you have an object made up of those particles, as long as the distance between those particles, the r, is really big compared to the size of the objects, then this law still holds true. Now, this diagram is certainly not to scale. The distance between the Moon and the Earth is on the order of 10 to the 8th meters. Okay, so it's a pretty large distance, where the radius of the Earth is on the order of 10 to the 6th. Okay, so we are talking like 100-fold difference here, a pretty big difference. But still, it is an approximation. It's good to sort of keep that in mind, but it definitely will be used as more of an exact value as we're talking. When you do have objects that have a size to them, you will need to make sure that you measure r with respect to their centers rather than their surfaces. So this, from say here to here, this distance here is never useful because there's lots of mass beyond each of those points. So just like we do with a lot of situations, we consider the center of mass of our objects to be the key point, and that's what we measure r from. That does cause a little bit of confusion with some situations. It means that if an object is at the center, or I'm sorry, at the surface of the Earth, it's really a distance away from the Earth. So even though it's touching the Earth, it is still a distance equal to the radius of the Earth away. And so that's something we'll have to pay attention to. So building off of that, the weight of an object now does change based on where in the universe that object is located. If the object is, say, on, we're talking about an astronaut that's on the International Space Station or orbiting the Earth or something like that, then that astronaut's weight is technically a little bit smaller because the weight would be found using this gravitational force, but because they're not on the surface of the Earth anymore or anywhere really near the surface of the Earth, this distance between the center and the object is now a little bit different. Okay, it's not equal to just the radius of the Earth. And so as that distance increases, the gravitational force decreases, and so your weight is a little bit smaller as you go further away from the Earth. Again, don't think about like traveling up to the top of a mountain and having significant weight loss. That's not the kind of distance we're talking about here, because the radius of the Earth is 6 million meters. Okay, and so in order to have an effect on your weight that's significant, you would have to move that sort of a distance away. And even the space station it's like on the order of maybe 10 to the fourth or 10 to the fifth meters away. So that's where it starts to be appreciable. But when you're on the top of a mountain, you're just changing your height by miles, which is maybe 1,000 or 2,000 meters. That's on the order of 10 to the third maybe, or 10 to the second maybe. It's just not affecting things. So everything that we've been talking about so far, where we've said, oh, the gravitational force is the mass of the object times 10, or 9.8, that still is going to hold true, and we'll show that in just a few minutes. But if an object is further away and you're asked to find the weight, you have to use this formula. You have to use the law of gravitational, universal gravitation, and take into account that distance in the calculation. All right, so how does your weight vary? How could we sort of come up with a different way of thinking about our G? So again, if you're near the surface of the Earth, it's still correct for us to say that G is approximately 10 or 9.8 newtons per kilogram, or that the acceleration of an object near the surface of the Earth is still 10 meters per second squared. Okay, that's still true. But if you get further away, it does vary a little bit. And we're going to derive this formula up here. As it says, this is not on our formula sheet, but at times we may be asked to state a value of this gravitational acceleration or the strength of gravity. So we want to make sure we understand it. It's a very easy idea. If gravity is the only force on an object, then if we were to draw a free body diagram for that object, the gravitational force would be pulling down or towards the center of the Earth, and so the net force would just be this formula up here. So I've changed my variables just a little bit in the last few slides here. Officially M1, M2, but a lot of times we'll use a capital M to represent a planet like the Earth, or maybe a large satellite like the Moon, and then a small m to represent the object that we are working with. If that doesn't work for you, if you can't write capital M's and little m's neatly enough to keep them straight, you can certainly use subscripts. There's nothing wrong with that. All right, so if we're in a situation where only gravity is the thing acting, like as if I drop a ball or something like that, what we want to notice is how the mass of the ball or the object cancels out, and so the acceleration is just the the gravitational constant times the mass of your planet, or whatever it is that you're kind of falling towards, divided by your distance from its center squared. So pretty simple derivation, but something where you want to be able to derive it. It's not on your formula sheet. Only the gravitational force itself is.